In this video, we deal with the problem of automatically tracking the tempo and the beat of music. Opposed to other approaches, we do not assume that the tempo is constant throughout the recording. Instead, we want to do beat tracking even in the presence of local tempo deviations. To this end, we describe a mid-level representation that captures the predominant local pulse. When humans listen to music, they automatically tap the foot along with the music. In beat tracking, this is exactly what we want to do automatically. For example, let us consider the following excerpt of a song.
He walks barely down the street with the people way down low. Ain't no sound but the sound of his feet. Machine guns ready to go.
Now, the beat tracking task is to automatically find the beat positions of the song as indicated by the red lines and the clicks in the following recording.
He walks barely down the street with the people way down low. Ain't no sound but the sound of his feet. Machine guns ready to go.
In this example, it is really easy to find the beats. The piece has a clear rhythm, the tempo is constant, and the beats go along with clear percussive onsets. For general music, however, beat tracking is not an easy task. A first problem is that the pulse level to tap along may not be clear. Different people may tap on different levels. In the case of Happy Birthday to You, one may tap or clap on the measure level. So, Happy birthday to you, happy birthday to you. The next final level is the so-called tactus level, which is typically the quarter note level. In our case, happy birthday to you, happy birthday to you. And finally, the finest level is the tatum level, the temporal atomum level, which refers to the fastest repetition rate of musically meaningful accents occurring in the signal. So in our case, this would be the 8th note level. Happy birthday to you, and so on. So for general music, the actual pulse level to be considered the beat level is not well defined and may be quite subjective. Another problem is that there may be tempo changes throughout the recording. The tempo may change smoothly or it may change suddenly. For example, what is the tempo of the following romantic piece of music? Try to tap along while listening. As you may have noticed, there are continuous tempo changes, making beat tracking really hard. In the middle, there is even a beat without any note onset. And after that, there is a significant change in tempo. So let us listen again to the recording along with the actual beats. Plotting the tempo for each beat, one obtains a tempo curve. This curve again indicates the continuous local tempo changes from beat to beat, as well as the sudden tempo change in the middle. I have to admit that the last example is quite extreme, but I want to make the point that beat tracking for general music is not yet a solved problem. Which pulse levels should be considered? How can one deal with local tempo deviations? Is note onset information enough for doing beat tracking? How can one actually extract note onset information? What happens if the onsets are played very softly, for example by strings? then the information the beat tracking is based on is rather vague. In the following, I want to give answers to some of these questions. In particular, I introduce a novel mid-level representation that captures predominant local pulse information. As our running example, let us consider a recording of a waltz by Dmitri Shostakovich. This piece has a 3/4 time signature, so there are 3 beats per measure. When listening to the following audio clip, please note that the first beat of each measure is actually played by the contrabass and other strings, which results in rather soft note onsets. In contrast, the second and third beat of each measure are supported by a snare drum, resulting in quite crisp onsets. Furthermore, to make the example more difficult, we have also continuously increased the tempo bit by bit. So, in this example, one may expect that finding the first beat of each measure is more difficult than finding the second and third one. The first step in most beat trackers consists in detecting note onsets, the start times of notes. Such note onsets typically go along with a change in the signal's energy and, in particular, with a change in the signal's frequency content. Therefore, using a short-time Fourier transform, we first convert the signal into a time-frequency representation, a spectrogram. Here, you actually see the magnitude of the spectrogram. Next, we apply a logarithm to the magnitude spectrogram. Such a logarithmic compression not only accounts for the logarithmic sensation of sound intensity, but also allows for adjusting the dynamic range of the signal to enhance the weaker spectral components, especially in the high frequency regions. Then we compute the discrete derivative of the compressed spectrum in a row-wise fashion, so for each frequency band separately. Since we are only interested in energy increases, only the positive differences are considered. In the next step, we sum up the positive differences in a column-wise fashion, which yields for each frame or point in time a single positive number. As a result, we obtain a curve over time, a so-called novelty curve. The peaks of the novelty curve indicate time positions where major changes happen in the signal's spectrum. So in some sense, these are the points of novelty. We further process the novelty curve by computing a local average curve, which is then subtracted from the original curve. After a further normalization, we obtain the novelty curve that is used for the further steps. As said before, the peaks of the novelty curve indicate points of novelty, which are good candidates for note onsets. Let us check this for our running example, the waltz by Shostakovich. You will hear the recording along with clicks that indicate the peak's time positions. This example illustrates that our onset detection works to some degree, but it is far from being perfect. In particular, you may have noticed that some of the expected onsets are missing, namely the ones corresponding to the first beats of the measures. Recall that these beats are played mainly by strings. This results in rather soft onsets that are hard to detect. Now, we are not interested in the onsets itself, but in the beats of the music. In beat tracking, one typically makes the assumption that beats occur in some kind of periodic fashion, at least within a certain time window. Based on this model assumption, it is reasonable to analyze the novelty curve in terms of periodic patterns. This can be done in many ways, for example using autocorrelation methods or comb filters. We use a Fourier-based approach for finding locally periodic patterns within the novelty curve. This results in a tempogram, which is similar to a spectrogram. This time, however, the frequency axis is not measured in Hertz, but in beats per minute, or BPM. To compute the tempogram, we consider for each time position a local section, or frame, of the novelty curve. In this case, the section corresponds to roughly 4 seconds of the audio signal. Then, to compute a single entry of the tempogram, a suitably windowed sinusoid of corresponding frequency, or tempo, is correlated with the section of the novelty curve. The entry is then defined by the correlation value. In other words, this value is the magnitude of a suitable Fourier coefficient. Here, you see another entry computed at time position 7.5 seconds and a tempo of 250 BPM. For each time position or column of the tempogram, we consider the maximizing coefficient. Each maximizing coefficient also defines a windowed sinusoid, a kind of local periodicity kernel. Each such kernel explains the local periodic behavior of the novelty curve. Or, in other words, each such kernel can be regarded as a periodic enhancement of a local section of the novelty curve. Now, instead of considering all these kernels individually, one crucial idea is to accumulate all maximizing kernels over time, so one kernel per frame. Using this overlap add technique, we obtain a single curve. We further process this curve by applying a half-wave rectification, setting all negative values to 0. As our final result, we obtain a curve we call predominant local pulse curve, or PLP curve. Let us have a look at the PLP curve and the original novelty curve computed for our Shostakovich example. The original novelty curve looks quite noisy. Many of the peaks that correspond to soft node onsets are small, blurred, or even missing. In contrast, the PLP curve shows a pattern of regularly spaced peaks. Furthermore, many of the peak positions in the PLP curve coincide with the positions of the most prominent peaks in the original novelty curve. In this sense, the PLP curve can be regarded as a periodicity enhancement of the original novelty curve. Let us listen to the Shostakovich recording along with the clicks for the peak positions. For comparison, we start again with the original novelty curve. Now, let us listen to the PLP result. This example shows that the beats corresponding to weak onsets have been recovered by the PLP curve. Also note that the PLP curve could perform the beat tracking well despite of the continuous increase in tempo. In summary, the novelty and the PLP curves have the following properties. The novelty curve indicates candidates for node onsets. However, soft onsets are hard to detect and may lead to extraction errors. Therefore, simple peak picking is problematic. The idea of the PLP curve is to enhance the periodicity of the novelty curve in a local fashion. By accumulating local estimates, the local periodicity kernels, one achieves a high degree of robustness to local extraction errors. Furthermore, the locality of the kernels allows for handling variations and changes in tempo. By means of the song Happy Birthday to You, we have discussed the issue of choosing a suitable pulse level. Let us come back to this issue by looking at a different example. Here you see the score of the first part of a piece by Friedrich Burgmüller. At the beginning there are 4 quarter note chords. Then, in the next 4 measures, groups of 16th notes dominate the piece, before it drops back to an 8th note level. Finally, measures 3 to 9 are repeated. Let us listen to a recording of the beginning of this piece. The tempogram of this audio recording reveals the tempo of the dominating pulse. In this example, one can observe high values for tempi around 105, 210 and 420 BPM. Recall that, when computing the PLP curve, we simply take the local periodicity kernel that corresponds to the maximum tempo coefficient for a given time frame. This may lead to a switch in the chosen pulse level over time. Actually, this has happened in our Burgmüller example, where in the first 12 seconds the kernel first corresponds to the quarter note level, then to the 16th note level, and finally to the 8th note level. We have seen these dominating levels already in the score. Let us listen to a sonification of the peaks of the resulting PLP curve. So, the PLP curve is not designed for making a specific choice of a particular pulse level. Instead, it locally chooses the pulse level that is predominant for a local section of the audio recording. In other words, the change of the predominant pulse level is captured by the PLP curve. However, prior knowledge may be easily integrated into the PLP concept. For example, by restricting the tempogram to a neighborhood of a suitable tempo, one can enforce a specific pulse level. For example, only allowing tempi from 50 to 150 BPM, one obtains the following PLP curve corresponding to the quarter note level. Similarly, one obtains a PLP curve corresponding to the 8th note level. Or to the 16th note level. Next, we demonstrate to which extent tempo changes can be handled by the PLP concept. To this end, we consider a recording of Brahms' Hungarian Dance No. 5, a piece with many sudden tempo changes. This is also reflected by the tempogram showing a predominant tempo of 180 BPM which jumps to 280 bpm and then drops back to 150 bpm. Let us listen to the audio excerpt corresponding to seconds 6 to 16 in the shown tempogram. Choosing the predominant pulse for each frame, the resulting PLP curve indeed captures, at least to some degree, the local tempo. This example also illustrates that the amplitude of the PLP curve does not relate to the signal's energy. Instead, the amplitude expresses some kind of confidence in the pulse estimation. This becomes obvious in the middle part, where the tempo changes twice within a relatively small time window. Since, in this example, the local periodicity kernels were chosen to have a duration of roughly 4 seconds, the PLP curve needs a couple of seconds before it stabilizes at a certain pulse rate. As a final example, we consider the beginning of the String Quartet No. 2 by Alexander Borodin. This is a difficult example. First of all, being string music, the onsets are soft and vague, so that the resulting novelty curve includes many extraction errors. Furthermore, the music itself is complex with respect to the rhythm, because there are syncopations, triplets, and so on. In this case, as we will hear now, the PLP curve does not yield meaningful results. However, one can stabilize the beat tracking result by including prior knowledge. First, one can again reduce the tempo range. In this case, we only allow periodicity kernels from 100 to 150 bpm. Or one may increase the duration of the kernels, for example from 4 seconds to 8 seconds. On the positive side, we have increased the robustness of our beat tracker. On the negative side, we have lost temporal resolution and some flexibility using these adjustments. With this video, our goal was to show that beat tracking and tempo estimation can be quite challenging problems, in particular for music with soft onsets, changing tempo, and rhythmic displacements. And music processing research is still in its infancy in automatically extracting and understanding high-level concepts such as the beat, the tempo, the time signature, the rhythm, or the groove of music. In this context, we have introduced a novel concept for extracting the predominant local pulse information from a given audio recording. Further details on this technique, as well as pointers to the literature, can be found in the cited IEEE paper. Furthermore, we have made a reference MATLAB implementation freely available for research purposes. Besides the PLP concept, our Tempogram toolbox also contains further functions related to tempo estimation and beat tracking.